Okay, good morning, everyone. So we've been talking about hydrogen atom stationary states. And last time I just quoted for you the result about the expectation value. So expectation value of the radial coordinate, r. And the answer, just to give you an idea, for a stationary state labeled by n, l, and m, turned out to be the Bohr radius, A0, divided by 2 times 3n squared minus L times L plus 1. L is the angular momentum quantum number. N is sometimes called the principal quantum number. And A0, remember, is the Bohr radius. Which is h bar squared over the mass of the electron times the electron squared, electron charge squared, which turns out to be 5.29 times 10 to the minus 11 meters. So I didn't calculate that, I just gave it to you, but let's do an example of calculating in the ground state what is the expectation value of a power of R. So what is expectation value of R to the N? Okay, so to do that, so here's what we're trying to calculate. 100 is the name of the state. R to the nth power. Okay, and we're going to be working in the position representation. So we're using completeness in position to write this as an integral over R and an integral over phi and an integral over cosine theta. Okay, and the thing we're taking the expectation value of is R to the nth power. Notice I'm using capital N rather than little n. And then we have the wave function squared, which is 1 over pi Bohr radius cubed e to the minus 2r over Bohr radius. So this that I've written right there is the wave function for this ground state squared. Okay, so this is not too hard to calculate. The first thing to notice is that the wave function of the ground state doesn't depend on the angles at all. So we can just go right ahead and compute the integrals over the angles. This is what we've otherwise called d omega, and that's just equal to 4 pi. Okay, so our answer for the expectation value is, once we cancel the pi's, 4 over the Bohr radius cubed times an integral that we still have to do from 0 to infinity dr of r to the n plus 2 e to the minus 2r over the Bohr radius. Okay, and then to do this integral, what we can do is a change of variables. Namely, we can write, let's let u equals 2r over a0, and du is 2 over a0 dr, and just plug those in. So notice what we're doing is we're using a new integration variable that is dimensionless. That's often a good idea. And so we get 4 over a0 cubed, a0 over 2 to the n plus 3. It's n plus 3 because there's r to the n plus 2, and then there's the dr. And then what's left over is integral 0 to infinity du, u to the n plus 2, e to the minus u. And that one is something you can just look up. That's n plus 2 factorial for n greater than or equal to minus 2. And it's infinity for n less than minus 2. It just blows up. That integral just blows up if n is too negative. Okay, so now we can make sort of a list of the expectation values of powers of the radial coordinate. First, let's do n equals 0. So for n equals 0, we're taking the expectation value of 1, that's r to the 0th power, which is, according to this, 2 factorial. Maybe I should write the general expression here by simplifying. So this is going to be n plus 2 factorial over 2 to the n plus 1 times the Bohr radius to the nth power. So as a check, since we're calculating the expectation value of a radius to the nth power, this should be a distance to the nth power, and indeed it is. So that's a good check. So getting back to the expectation value for n equals 0, this is 2 factorial over 2 times the Bohr radius to the 0th power, which is 1, of course. And so that's just 1, which is a check because that's just saying that we normalized our wave function correctly. The expectation value of 1 should be 1 if we have our state normalized correctly. Okay, and if we plug in n equals 1, now we're doing the expectation value of r. That is a special case of this up here, where we're plugging in n equals 1 and L equals 0. So the answer should be just 3a0 over 2. Let's see if that's what we get. So according to this formula, we get 3 factorial over 2 squared times the Bohr radius to the first power, which is indeed 3/2 a0. That's again just checking what I'd already mentioned to you at the beginning. So now let's try n equals minus 1. That will be useful for us later on. So now we're using the expectation value of 1 over the radial coordinate, which is 1 factorial over 2 to the 0th times 1 over the Bohr radius. 2 to the 0 is 1, so this is just 1 over the Bohr radius. Okay, so notice that the expectation value of 1 over r is not equal to 1 over the expectation value of r. In other words, the process of taking an expectation value does not commute with normal algebraic things like taking reciprocals or taking powers. Okay, for n equals minus 2, 1 over r squared, expectation value, is 2 over a0 squared. And then if you do n equals minus 3, 1 over the expectation value of r cubed is actually infinity. It blows up. That's just because this integral that we did here is blowing up when n is less than minus 2. Okay, and so for the same reason, the expectation value of 1 over r to the 4th, the expectation value of 1 over r to the 5th power, etc., those are just all equal to infinity. They just blow up. Okay, let's look at some positive powers. So for n equals 2, when we plug into our formula, the expectation value of r squared is n plus 2 is 4 factorial divided by 2 to the n plus, what was it? N plus 1 So that's 4 factorial over 2 cubed, which is equal to 3 times the Bohr radius squared. Okay, and then you can continue on like this. The expectation value of r cubed turns out to be 15/4 Bohr radius cubed. The expectation value of r to the 4th is 45 over 4 Bohr radius to the 4th, and you can keep going as much as you want. So one application of this is, what about the uncertainty in the radial coordinate in this ground state? So remember, the general formula for the uncertainty of an operator is you take the expectation value of the operator squared minus the expectation value of the operator squared. We worked both of those things out. So this is square root of 3a0 squared minus 3/2 a0 squared, which is otherwise known as square root of 3 over 2 times the Bohr radius. Again, this had to have units of distance, so it had to be some number times the Bohr radius, and it just turns out to be square root of 3 over 2. So other things we can ask about are things like, what's the expectation value of the position vector? And notice that's 0. So if we take the expectation value of the position vector, that has to be 0 just by symmetry, because there's no special direction in this ground state. The ground state is spherically symmetric. And so if we were to compute this expectation value of this vector and it pointed in some direction because it was non-zero, then I could ask you, just why doesn't it point in some other direction that's equally as good? And the only way that can be reconciled is if it's 0. And similarly, that's true of any vector expectation value in the ground state. So for example, the expectation value of momentum vector, we really don't have to do a calculation. We just notice that there's no special direction. So this has to be 0 as well. Okay, by the symmetry argument. But one thing we could do is we could say, instead of position, let's ask, what about the expectation value of momentum squared? So that's not a vector. So the argument about no special direction doesn't work, and we actually have to do a calculation to find out what's the expectation value of the momentum squared. Okay, so let's just do it. And we will do it using, again, the position representation. So remember, in the position representation, p squared is represented by minus h bar squared Laplacian squared. So that means expectation value of p squared is, we're going to integrate over all positions. Again, remember, when you integrate over the radial coordinate, there's the r squared factor. Don't make the common mistake of forgetting that. And then there's the integral over angle, d phi, and the integral over cosine theta from -1 to 1. And then we have psi 1, 0, 0, complex conjugate. That's the wave function of the ground state. And then our operator, minus h bar squared Laplacian squared, multiplying psi 1, 0, 0. Okay, so notice the operator acts only on the wave function when you're computing this expectation value, not on the wave function complex conjugate that goes on the other side. So now we just have to plug in these things, and we remember, okay, the wave function of the ground state is 1 over the square root of pi Bohr radius cubed, e to the minus r over Bohr radius. And so then we have to plug that in here too. So there's a minus h bar squared. The Laplacian has a factor 1 over r squared, partial r, r squared, partial another r, 1 over square root pi a0 cubed, e to the minus r over a0. Okay, and there are also theta and phi derivative terms, which you could write in terms of L times L plus 1, but L is equal to 0 for the ground state. Or another way of saying it is there are theta and phi derivatives which vanish. And they vanish again because we're in an L equals 0 state. So due to L equals 0 state. If you were calculating this for a state that had non-zero L, then those would contribute. Okay, so we have to do two things here. First, we have to take these derivatives, and then once we're done, we need to multiply by this, and then we need to do the integral. All right, so let's go ahead and do that. So first, let's pull out all the constants that are in front here. So there are two factors of 1 over square root of pi Bohr radius cubed, and there's a factor of minus h bar squared. And then there's going to be the usual factor of, from here, 4 pi, because none of the integrand depends on theta or phi. So that just is going to do the usual 4 pi thing. And so we get minus h bar squared times 4 over Bohr radius cubed. And then what's left is the r integral. Okay, now notice this 1 over r squared is going to nicely cancel this r squared. So we don't need to write them down. And then what's going to happen is we have d by dr, r squared, d by dr, e to the minus r over a0. Oops, and then I forgot this. This has another factor of e to the minus r over a0. So I should put that in here. Okay, so to take these derivatives, first of all, this derivative is minus 1 over Bohr radius e to the minus r over a0. And then when I do this derivative acting on that with the r squared, we get minus 1 over Bohr radius 2r e to the minus r over a0 minus r squared over a0 e to the minus r over a0. You can see that this will get pretty hard when you're doing something other than the ground state where the wave function is much more complicated. But anyway, putting all of that together, this is this integral times minus 2r over a0 plus r squared over a0 squared. Okay, and that whole integral you can, I'm not going to do it, but it turns out the answer is minus a0 over 4. And so when we put that all together, the minus signs here cancel, the 4's cancel, and we just end up with, so the expectation value of p squared is h bar squared over the Bohr radius squared. Okay, so the units check. because h bar squared over a distance squared is a momentum. And so it's always good when you're doing a calculation like this to make sure the answer has the right units. That way you know you haven't dropped a factor of, say, the A0 or something like that. And so now that we've got this, we can do some checks. One check is the units that we've just done. And another check is you can put what we found together and calculate the expectation value of the Hamiltonian. Because the Hamiltonian is p squared over twice the mass of the electron minus e squared times the expectation value of 1 over r. And we found that p squared over twice the mass is h bar squared over twice the mass, A0 squared. And now if we plug in what A0 is, okay, this turns out to be mu e to the 4th over 2h bar squared. Oh, I forgot one other important check about p squared. Namely, p squared is a positive definite operator. And so this came out positive. Actually, it was this minus sign times that minus sign that made it come out positive. But that's another good check, is that this turned out to also be positive. So. Okay, so that made this quantity also be positive. And then calculating the other term, minus e squared over the expectation value of 1 over r is minus e squared over A0. Notice it wasn't obvious maybe immediately that this thing and this thing could be added together. But what we can do is write them in terms of the same quantities. So we're going to get rid of A0 again by plugging in what it's equal to. Okay, and this turns out to be minus mu e to the 4th over h bar squared. So it's the same quantity, but with a different factor in front. And now we can combine them to get the total is minus mu e to the 4th over 2h bar squared, which is minus 1 Rydberg. Rydberg's a unit of energy, otherwise known as negative 13.6 electron volts, which is in fact obviously the correct expectation value for the Hamiltonian, because the Hamiltonian acting on the ground state just gives minus 13.6 electron volts. So that has to be its expectation value also. Okay, any questions on that so far? All of that was for the ground state of hydrogen. So in principle, I could ask you to do this for, say, one of the first excited states, and the algebra would be a little bit harder, but the ideas would be the same. All right, so let's do a little bit more with dimensional analysis. So one thing you might say is that up to a multiplicative factor, you might have been able to guess, for example, things like what was the Bohr radius. So if you were to estimate, okay, what's the size of the hydrogen atom, which is given by this Bohr radius, which is h bar squared over mu times e squared. One way of thinking about it is that's a quantity that you can form that has units of distance built out of the quantities in the problem, namely h bar and the mass of the electron and the charge on the electron. And it satisfies what you might expect it should satisfy. One is it goes to 0 if h bar goes to 0. So h bar goes to 0 is the classical limit. And this is saying in the classical limit, the hydrogen atom should just collapse down to a point. That's actually what we mentioned on the first day of class. This is this catastrophe in classical physics that charged matter would just collapse. Okay, another thing is if you take E very large, if you take the charge on the electron to infinity, then the force between the proton and the electron becomes very large, and the thing should again collapse down to a point. So the Bohr radius should go to 0 in that limit, and sure enough, that's what this is telling us in the denominator. Okay, and then the same thing would happen again if you take the mass of the electron goes to infinity, then it's very heavy and it can't escape from the proton. So it might look like, oh, we could have just guessed up to maybe a factor of 2 or something what the Bohr radius was, but that's not exactly right because it turns out there's another dimensionless quantity that you can make, and then you could multiply this by that dimensionless quantity. So, Bud can make a dimensionless quantity. Dimensionless means no units. And that dimensionless quantity is called alpha, and it's equal to E squared over h bar times the speed of light. So you can check that thing has no units, and numerically it's approximately 1 over 137.036 something something something. Okay, where so c is the speed of light. Okay, and so we could multiply A0 by any power of alpha, and that would also be a dimensionless or something with units of distance. So for example, another length scale that you could make would just be this alpha, also known as the fine structure constant, times the Bohr radius. And this is actually given a name. This is called the reduced Compton wavelength of the electron. So the symbol sometimes looks like a lambda with a slash. This is reduced Compton wavelength. Of the electron. Notice it doesn't really necessarily have anything to do with the hydrogen atom, because the numbers that go into it just have to do with the electron and light and things like that. Another way of writing it is that it's h bar divided by the mass times the speed of light. So that's a unit of distance that's much smaller than the size of the hydrogen atom. So what distance scale should we associate this? What physics is it that's associated with this if it's not the hydrogen atom size? And it turns out to be the distance scale at which electron-positron pair production becomes important. So at very, very short distances, much smaller than the hydrogen atom, you have to worry about virtual electron-positron pairs popping out of the vacuum. And this is the scale at which that might occur. So to understand why that would be the scale, the distance scale, okay, suppose we confine the electron to a very small scale like this. So suppose confine electron to some range delta x. Okay, so the uncertainty principle tells us that delta p should be h bar over delta x, very roughly. We're not going to worry about factors of 2 today in this analysis. And if delta p goes like that, then delta E for a relativistic particle is the speed of light times the momentum. So this should be true for a relativistic particle. Okay, and so if you put in delta X is much, much less than the reduced Compton wavelength, which is h bar over mu times c, then you will find delta E is much, much greater than twice the mass of the electron times the speed of light squared. Now the mass times of the electron times the speed of light squared is the energy needed to make an electron. So this is the energy needed to make an electron-positron pair, just from taking into account their rest energies. So the interpretation of this is, if we try to localize an electron, meaning confine it to a scale smaller than the Compton wavelength, then the pair production of virtual positrons and electrons becomes important. Which means that all of the quantum mechanics that we've done would not be appropriate anymore, would be the wrong thing to do. We've just done the wrong calculation. So why is it that we don't have to worry about that? It's really because that's a very large energy compared to the actual energy of the hydrogen atom. So remember, 1 Rydberg, the actual energy of the hydrogen atom is, let's write it various different ways. So the way we originally wrote it looked like this: mu e to the 4th over 2 h bar squared. But now I'm going to write it as mu times c squared. That's the rest energy of the electron times 1/2 times e squared over h bar c squared. Okay, so the rest energy of the electron is 0.511 MeV. And then there's the 1/2. And then this is, this right here is the alpha squared. Okay, so this is rest energy of the electron. And so really the point here is that alpha, because it's a small number and then it's getting squared, makes it a very small number. That means this Rydberg is very small compared to the energy that you would actually need to start making positrons out of nothing. So another way of saying this is, how big are relativistic effects really? The answer is going to be that they're very small, but let's check that out. So how big are relativistic effects for hydrogen atom? So first, let's remember the non-relativistic Hamiltonian, the one we've been using, relativistic. That was p squared over twice the mass. And then the relativistic version, if we consult Einstein's theory of special relativity, that would say, instead of p squared over 2 mu, we should write down this expression: speed of light times p squared plus mu squared c to the 4th. So that comes directly out of special relativity. And then if we want, we can subtract off a constant. It never hurts to subtract off a constant quantity. and we'll subtract off the constant rest energy. Okay, so now let's rewrite this. We can rewrite it like this. The square root, we can pull out a factor of mu c squared and write the rest of it as square root of 1 plus p squared over mu squared c squared. Okay, and then we recognize for small p, this number is very close to 1, so this term is trying to cancel this term. But let's see how close it comes to canceling. So we can do that by expanding the square root like this. Oops. So it's minus p squared squared over 8 mu to the 4th c to the 4th. And then this keeps going. And so really what I've done here is I've used the binomial expansion, which says square root of 1 plus x for small x is 1 plus 1/2 x minus x squared over 8. And because we're expanding in a small number, we're not going to worry about what comes next. But of course, the binomial expansion goes on forever. Okay, so now if we look at this, we see what's going on is this term's going to just cancel this one. So they're both going to go away. This term multiplied by that is going to give us the non-relativistic answer. And so the leading relativistic correction is just going to be this thing times this factor out front. Okay, so let's write that down. H relativistic equals p squared over twice the mass. That's the non-relativistic answer. And so the correction is minus p squared squared over 8 mass cubed c squared. And I'll write plus dot 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 to remind us there are terms we're neglecting. Okay, and so this, all of this is the change in the energy due to relativity. Now, it turns out that this calculation I've just done is not quite right because it doesn't include spin. And in Physics 661, we'll understand that in more detail. So this doesn't include spin. And when you put in the spin effects, it turns out to be of the same order as this. So really, this is only good as an order of magnitude estimate. But let's go ahead and do the order of magnitude estimate just to see how big it ought to be. Okay, so we're going to estimate the magnitude. Okay, and so delta E is minus the expectation value of p squared squared over 8 mass cubed c squared. Okay, and very roughly speaking, we're going to say that the expectation value of p squared squared is the square of the expectation value of p squared, even though that's not quite right. We're only interested here today in getting the order of magnitude, though. Okay, so this is h bar squared over a0 squared squared over 8. And probably we shouldn't even be worried about the 8 because this is just, again, a rough estimate, but we'll keep it anyway. Okay, and so now our strategy, again, is to rewrite everything in terms of, to eliminate the Bohr radius. So this is minus h bar to the 4th mu e squared over h bar squared to the 4th over 8 mu cubed c squared. And when we do the canceling of mu's, this is minus mu e to the 8 over 8 h bar fourth c squared, which we can write as minus mu c squared, 1 over 8 e to the 8 over h bar fourth c to the fourth. Why are we writing it that way? We're writing it that way because this is the fine structure constant to the fourth power. And actually, I forgot here a 4 exponent there. Okay, so we can write this as, and I'm writing a squiggly equal because again, this is just an order of magnitude estimate, minus mu c squared 1 over 8 alpha to the fourth power. So we're not going to do it today because we don't have the tools involving spin and other relativistic effects. But let me just tell you that a correct analysis, which we will do in Physics 661, instead of having minus 1 over 8, is actually 1 over 2n for states with principal quantum number n and L equal to 0. And it turns out it completely cancels for states with L not equal to 0. So that's a surprising thing. And there's no way for us to tell from what we've done, what we've written down today, that cancellation would occur. But anyway, just going back to the order of magnitude estimates, what is that telling us? It's saying the change in the energy level due to relativity should be proportional to the fine structure constant squared, because there's alpha to the fourth here, but the actual energy level only had alpha squared here. Okay, so we're getting an extra factor of alpha squared times the energy divided by n. Okay, so this is known as fine structure. And so now we see the whole reason that we've been able to get answers that are even close to being correct is simply because alpha is very small, so that this correction is very small. If alpha had turned out to be 137 instead of 1 over 137, then this would have been a huge correction coming from relativistic effects, or equivalently coming from electron-positron creation. And everything we would have done would have been wrong. But fortunately, it's okay. Okay, so single particle, non-relativistic quantum mechanics works because alpha is much, much less than 1. Okay, so there are other things you can do with this alpha and the fact that we know its value. One thing we can do is you can worry about things like, what's the velocity of the electron? And I put that in quotes because how do you define velocity in quantum mechanics? One way to do it would be the square root of p squared divided by the mass. Square root of p squared is like the characteristic momentum, and we're dividing the momentum by the mass to get the velocity. And so we worked out that p squared, the square root of p squared was h bar over a0. And so this would be h bar. Again, our strategy is to eliminate a0. And so this is e squared over h bar, which is the fine structure constant alpha times the speed of light. Okay, so in other words, if you define beta to be the velocity of the electron divided by the speed of light, that's approximately alpha, which is 1 over 137. So that's telling you that the electron in a hydrogen atom is not very relativistic because its velocity is small compared to the speed of light. Okay. One more thing we can do for today with what we've learned about the hydrogen atom is consider the spectrum of light that would be emitted between transitions. So this is light emitted or absorbed by atomic hydrogen. There's also molecular hydrogen, where hydrogen is bound into molecules H2. But let's just worry about atomic hydrogen. And so you have some state N and some lower state N prime. And if you transition between those states, you will give off a particle of light, a photon. The photon's energy will be the difference in energy levels. So you can write that as h bar times omega n prime for that transition. It will just be the energy of the state n minus the energy of the state n prime. Okay, and so plugging in what we've learned about those energy eigenvalues, omega n prime, the frequency of the light, is going to be 13.6 electron volts divided by h bar times minus 1 over n squared plus 1 over n prime squared. Okay, the 1 over n squared comes from here. The 1 over n prime squared comes from here. So for example, there's something called the Lyman series of spectral lines. The Lyman series just involves transitions to the ground state, which means the ground state is n prime equals 1. And so we can just predict that the angular frequencies of that light is 13.6 electron volts over h bar times 1 minus 1 over n squared, where n is the other state that you're going to, which could be anything except 1. So it can be 2, 3, 4, up to infinity. So now if you plug in the numbers, you can find the wavelengths of those light photons. The formula is 2 pi c over omega. Okay, and so when you plug in the numbers, you get, for example, for n equals 2, it's 1.216 times 10 to the minus 7 meters. And that's known as the Lyman alpha line. So that's used in experimental astrophysics quite a bit, because there's not a lot, but there's nothing but atomic hydrogen mostly in outer space. And so the light is constantly hitting hydrogen atoms, and that's the most prominent transition, is the Lyman alpha line. And then you can do lambda 3.1, lambda 4.1, so lambda 2, 3.1, etc. But the shortest the wavelength can be, the limit is when n is very large, and this is 9.118 times 10 to the minus 8 meters. Okay, so that's the shortest wavelength. This whole series of transitions is known as the Lyman series. And so this is the Lyman limit. It's the shortest wavelength or the most energetic photon that you can get from transitions in atomic hydrogen. All right, so we are out of time for today, but we will continue saying a few more things about hydrogen next time, and then we'll be spending the rest of the semester talking about some more details about angular momentum. All right, any questions? All right, if not, then I will see you all on Friday, virtually see you all on Friday.
Thank you.
Okay, have a good day.